All right. Hello, everyone. I'm Tanishka Wagh. I'm a third year student now in Mahindra University studying computation and mathematics. I'm also in the diploma level of IIT Madras's BS degree. Uh, so I've done my diploma in data science, and now I'm in my second term of the diploma in programming. Today I'll be talking about the beta distributions and the Dirichlet distribution. Uh, what qualifies me to be talking about this, given most of you are probably just as old as I am, is that I've done an internship at IISER Pune, wherein I was working under a professor, Professor Bhagwat, uh, wherein I basically did a reading project on Bayesian inference. So let's get started. So what we're going to be doing in this session is constructing the idea of Bayesian thinking. You don't need to know what that is. I'll explain it. We'll be constructing the beta distribution and the Dirichlet distribution, and we're going to see a little bit of geometry so that it's a little bit more intuitive to everyone. Uh, so you might have heard this fact that the life expectancy in 1947 in India was 32 years. So, and every time I heard this fact when I was younger, uh, much younger, was that does that mean 32-year-olds were dropping dead like all the time? And that's and I realized that that can't be true, right? So what is happening here? Well, we could take a step back and think about what is the expected what was happening in 1947, right? What is our prior knowledge of that time? We know that infant mortality rates were very high. Malaria, polio, uh, smallpox were very common because vaccines weren't a thing. And we start to realize that a lot of kids were dying, right? A lot of kids were dying during birth. A lot of infants were dying. So the fact is that the people weren't dying at the age of 32. A lot of babies were dying, and once you kind of got through the younger phase of your life where your immune system is not as developed and whatnot, you had a much better chance at living. So the median age of death was not probably 32. It was probably less, either very, very less. So it's a bimodal distribution, right? It's either you die when you're very young or when you're very old. So rather grim place to start the conversation, but gets the point across. We see this. So what we've done here to get a better sort of idea of what was happening is that we used our prior beliefs, which is the prior knowledge. For example, the infant mortality rates, the fact that vaccination wasn't widespread, and we use new data, which is this 32 years life expectancy rate, and we form our current belief. So the basic idea here is that we use new data not in isolation or to replace our prior information, but to update our prior information. So now the question obviously arises, how do we update it and how much data do we truly need? Because life expectancy here obviously was, I'm sure there was some sort of census that happened, and large amount of data means more certainty. Uh, but exactly how much data do we need for a certain probability model? Here, the probability model was simply taking the mean of the ages of death. But how much data do we need for a certain type of probability model? That's the idea here. So that's where we will take another example to illustrate another thing. So let's do a little bit of a poll here, perhaps. Imagine there's a rating system where you get to choose either that a product is good or bad. Let's think about it like a YouTube video, for example. Say it's just thumbs up or thumbs down, right? Uh, So we'll turn this into a bit of a percentage kind of reading, which again is a sort of mean reading, right? And we have two products, or let's say videos. One which has a 90% rating and it has 10 reviews, and one which has 85% ratings but it has 1,000 reviews. Could we see a show of hands of who would choose the 85% reviewed video over the 90% reviewed video? Just raise your hands if that's okay. All right. All right. I see some thumbs up. Okay. Yeah. So okay. Some of us are saying 90. So that's what I'm. So here the thing is, when you're taking up, we're looking at say 90% of the population is saying that this is a good video. It doesn't necessarily. We can't be very sure, right? So say all the friends of the YouTube creators came down to the video and gave all these likes, and only one person said it was a bad video, but that one person was a genuine viewer. It's more likely that that video is not that rating is not very reliable, right? So that's what. So when we're taking this sort of mean, we need to understand what we need to quantify how reliable this source is, this rating is, right? So we'll try to quantify this certainty of the probability being right. To put it quite simply, we're going to look at the probability of a probability being right. So let's model this into, let's take the number of good reviews to be n. Actually, this will be n, and this will be m. So the percentage reading is just right here, p equals to n by n plus m into 100, right? But let's keep it as a probability rating. Like I said, we're trying to estimate the probability of having a good experience, right? So let's try to model this using random variables. Random variables for the people in the foundation level who haven't done, say, stats 1, stats 2. Actually, we had, I'm sure we've had some amount of random variables working here and there. But basically, we're going to take variables and try to see what sticks. Okay. So let's take x to be the actual probability that we will have a good experience. As I go down, I'll change the notation a little bit. I'll take x equals to p here, p. So this will just be x. And n be the number of good reviews, right? So we'll use Bayes theorem to kind of model this. What we're trying to find out is f denotes the probability density function or distribution function, depending on whether it's a whether it's a continuous variable or not. And so we take f of, so the probability that the probability of having a good experience is the probability that we calculated here. Oh, it's not. Let's just do this. Okay. So probability that the actual probability is our estimated probability. So this is our estimated probability, right? Given that we've gotten a certain number of good reviews. Okay. So we'll use Bayes theorem to do this because we know what here, so the likelihood we'll be able to get easily, basically, because okay, let's let's just hit it. So Bayes theorem has a bunch of parts. So it's the posterior is equal to, posterior is just probability of A given B is equal to probability of B given A, which is the likelihood, and probability of A, which is the prior, divided by the probability of B. I want you to look at this formula in a slightly different way that we have been looking at it for a long time. This is what we're trying to achieve. This is what new data we have. Okay, because we're able to. So this is our prior belief, right? These are the things that we do know, and or we have assumed, and this would be our new data. So that's the same thing, right? So the new data is the number of good reviews that we've gotten, and oh, this is wrong. Supposed to be. Just give me a second. Oh, that's not right. Excuse me. Sorry about that. Yeah. So this is our so this the first part, the likelihood function, is simply a binomial function, right? You can either have a good review or a bad review. It's kind of like flipping a coin, but the probability is not half and half. The probability here we'll say is x. That is what we're modeling, right? So the binomial distributions from a PDF is given by n plus m choose n, which is the number of ways in which you can get heads or tails. So you can get, say you have three, you're flipping three coins and you can get heads, 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 tail, heads, 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 tail. But if you're thinking about the number of ways in which you can get two heads, that would be heads, heads, tail, heads, tail, heads, tail, heads, heads, right? So there's three ways. So we use that, we see that as a combination. So that is this combination, n plus m choose n. That is the number of positive reviews out of all of the reviews. And then we're saying that the probability of getting a good review is x, right? So that is, so the probability of getting that is kind of, we take the number of good reviews that came in as the exponent, and the number of bad reviews will be obviously 1 minus the probability. So, okay, a little nervous here, but okay. So we know the binomial distribution. This is just that. And then, so we will look at the prior information. So we'll assume here that every review is like as equally likely. So we'll say that getting a bad review is just as likely as getting a good review. So that is just uniform, right? Uniform 0, 1. So this one. Oh. Yeah. So that is just the PDF of which is 1 by b minus a. So that's just 1. So we can, and then the marginalization, we can kind of ignore the marginalization in some ways, simply because the numerator here will have this term x raised to n and 1 minus x raised to m, and the denominator, which is the probability that the number of good reviews is the number of good reviews that we have observed, is we will have this the term in the denominator as well. So since it is proportional, we can kind of see it as a constant. So simplifying this, so this is the binomial distributions PDF. This is the uniform distributions PDF from here, and this is the marginalizations PDF here. This is somewhat of, you can see this as a, it's a continuous variable because we don't know how many reviews we'll get. So which is why we're using an integration sign here. But again, like I said, we can take it as a constant because this is proportional to this. So basically what we get here is 1 by c x raised to n, 1 minus x raised to m. So you'll see that this looks very similar to the beta distribution if you've seen that so far, since we have some foundation students. I'll just show that I'll just tell you that the beta distributions PDF is this. So it's x raised to a alpha minus 1 times 1 minus x raised to beta minus 1 divided by b of a alpha comma beta, which is a normalization constant. It just it makes sure that the function is between 0 and 1, basically. So what we've done here is we've taken sort of a binomial distribution, which is we either get either get a good review or a bad review, and we have multiple reviews, each of which is independent of one another. And we've found the probability of our estimate to be correct. So, and this is exactly what the beta distribution does, right? So we've found that so we've constructed the beta distribution as the probability of a probability of something being right, and that something is a binomial distribution. Okay, binomial distribution's probability. So we can, so this is for a heads or tails kind of situation, right? But say you have uh, so say you have a good, okay, or bad rating, or say you have a 5-star rating scale, so we would have 5, right? That's not a binomial distribution, and we can't model that as a binomial distribution, which is where we'll see that our beta distribution fails, because here we could just see how many positive reviews we've gotten, which is n, which is n and m, right? And we could input that into the beta distribution. We'd add 1 to it, and we could input that into the beta function, and we would get the probability that our estimate is right. But we can't do that when we have multiple reviews, right? So if we have good, okay, or bad, we would have n, m, and say o, right? We can't enter that into the beta distribution, obviously. It only has 2 parameters. So can we extrapolate it to multiple dimensions? And turns out we absolutely can, and that is what the Dirichlet distribution is. So if you ask me in very simple terms to explain what the Dirichlet distribution is that it is the multiple dimension cousin of the beta distribution, basically. So let's try to see if we can do the same steps again and get to Dirichlet distribution. So we take the new data, which is how many good, okay, and bad reviews that we've gotten, which is n1, n2, n3. We also make a model. So probability distributions, we are assuming that it is the mean of n. So we're assuming that the probability that we'll have a good experience is n1 by n1 plus n2 plus n3, right? So this is just 1 plus n2 plus n3. This is our assumption, right? This is a probability model. We've just assumed for it to be true and widely true, or say the gospel truth, but that may not necessarily be true. Which is why we need these beta and Dirichlet distributions to kind of model how accurate we're being. And turns out that in most situations, this sort of modeling is not very accurate, or not the most accurate that we can be. So that's what we're going to be looking at now. So P1, like I said, is n1 by n1 plus n2 plus n3. P2 is again n2 by n1 plus n2 plus n3, so on. And then we're going to take a prior belief. So here we just took it to be uniform 0, 1, right? That was assuming that both a good review and a bad review are equally likely. Here we can kind of choose, well, we can choose it there too, but here I'll be showing you how we can choose that. Say we're assuming more good reviews than bad reviews, because when you look at the average YouTube video, I'm sure you'll see that people are more likely to leave a good review than they are to leave a bad review, or rather they're more likely to send in a thumbs up than a thumbs down. So we can kind of, so alpha is the same space as n. So think of it as the new data being in the same space, being taken from the same space as the old data, or rather our prior beliefs or what we know is true. So alpha is like your assumption or your best guess of how how you think that the distribution is going to be. So if I think that 1/3 of the people are going to leave a good review, let's say half the people are going to leave a good review, uh, two 1/3, 1/4 are going to leave a bad review, and 1/4 are going to leave a good, okay review, right? So what I could do simply is make alpha 2, alpha 1 2, and alpha 2 1, and alpha 3 also 1. So you can see that the ratio kind of depends. So same probability kind of mean that you have to take, and the ratio will be your assumption of what the ratio will be. Uh, so also we obviously need all the probabilities to add up to 1. P1, P1 plus P2 plus P3 needs to be equal to 1. So let's take the same function that we did before. And so now this is not a binomial distribution. This is going to be a multinomial distribution, which is again the like higher dimensional cousin of the binomial distribution. You don't need to know exactly what it's doing. I just want you to focus on the fact that it is a function of the product of the probabilities raised to our new data. And the prior, which is our prior information, is also, this is going to be modeled as something called a Dirichlet distribution. So you kind of need to use one Dirichlet distribution to define another one. But so if for now, I just want you to again look at the fact that it is a function of our prior beliefs so our prior beliefs and the probability distribution. Okay, so this we can see that it's proportional to this into this, right? Obviously these you can think of as constants. Again, they're not actually constants, but this will be proportional to this, and this will be proportional to this. So you can look at it as constants, or kind of avoid them when you're, at least when you're looking at simply the proportionality of it. And we can see that our old data, or our assumption, and our new data, which is our what we've observed through, say, experiment, are both involved in this measure, right? So what are we measuring again is so this is the probability that our so n1 by n1 plus n2 plus n3 is actually the correct uh, probability. So again, this is not actual probability that we've found out. This is a model, right? Finding the mean is a model. So is finding the median or finding the mode, for example. So we could have taken up either one, and then then x's value would obviously change. But for now, we've taken mean. So what this is doing is it's telling us how much the mean, mode, median is accurate, right? So we found that this accuracy is a function of our old and our new data, and that's exactly what we wanted. So to formalize it, we have this thing called the Dirichlet distribution, and we can see here that, so this is how the Dirichlet distribution's PDF is uh, written, or rather defined. Uh, it's a product of all of the probabilities, right? So this is a kind of a probability, because it does come from 0 to 1. Actually, this is not open interval, this is closed interval. And obviously, again, needs to, all of them need to sum up to 1. So we can see here that so here we have alpha I plus ni, right? So if we just substitute that in, we can see that our distribution, our accuracy function so let's call it an accuracy function, it is modeled by this distribution. So we can, and after simplifying, considering this and this, we see that our accuracy function, I'm calling it an accuracy function, it's not an actual accuracy function, it's a bit of my crude way of saying it, is exactly the same when you substitute this value, this value of the old data plus the new data. And so we can finally say that the probability that our predicted distribution, which is P, this can be, again, like I said, mean, median, mode. You want to make your own probability distribution, or assume different distributions. The world is your oyster. You can do whatever you want. And this is all, as long as P1 plus P2 plus P3 equal to 1. This is not necessarily mean. So the probability that this distribution, given the data that we've seen and our prior beliefs, that is correct, is a Dirichlet random variable. So what we're saying is that we can model our accuracy function as a Dirichlet random variable. Here we took 3 variables since it was easier to show, but without loss of generality, we can extrapolate it to just Dirichlet alpha 1 plus alpha n1 up to alpha n and nn. So what we've done basically is we found a way to model the accuracy of our probability being right for not just 2 variables, which would be the beta distribution, but for any n number of variables, right? So if you had a 10-point rating scale, you could still do this. If you had a 100-point rating scale, you could still again do this. But so we have a way. So this basically gives us a way to update our beliefs, right? But what does this mean geometrically? So let's take P1, P2, P3 and put it on a Cartesian plane, right? Let's just look at, let's do this here. For now, let's just do it with 2 variables. So P1, P2, we're back to our kind of beta distribution thing. Now, we could say that P1 is equal to P1 plus P1 comma P2, but we also know that P is just equal to P1 comma 1 minus P1, right? So do we really need 2 coordinates for each variable? We don't. We can simply put this on a line, right? So say this is our 0 to 1, and say we've collected the data and we found that there are 40 people saying that this was a terrible video, I didn't like it, and there's 60% of the people who are saying that, okay, this is a good video, so they give it a thumbs up. So where would we find ourselves? Where we would find ourselves somewhere here, right? So we'll assign this coordinate to P1 equals to 0.6. Okay, so basically every point on this line now holds a sort of somewhat of a state of not a state per se, but a probability, right? So basically we are now able to see a one-dimensional shadow of 2 variables. So basically any kind of probability that you would assume, you can find on this line, right? But this is for 2 variables. So how would you do it for 3 variables or even more variables if you have the computing power, let's say? That would get you to a triangle, right? So if you have 3 variables, you'll get a triangle. And we'll see how this triangle looks and kind of works. So again, we have the same A and B, good, bad sort of situation, but now we also have an okay situation, right? So what do we do now? So obviously here we saw that the coordinate of getting just all good reviews. So say we have an incredible video and everyone's given it a thumbs up, right? So we would be at 0, 0, or just 0 because we're just on the x-axis. And So the example that we saw would have been 0.6, and say it's a terrible video, nobody likes it, all of them have given us a bad review, we would get 1, right? So in on the xy coordinate plane, it would be 0, 0 and 1, 0, right? But the um, what would the coordinate of the C vertex be, right? Say we had a weird video somewhat, let's call it diabolically made, and so this point would have to be at an equal distance from good and from bad, right? So we need to be able to define a probability where nobody has given it a bad review, everyone's given it either a good or an okay review, or nobody has given it a good review and everyone's given it an okay or a bad review, right? So and those probabilities, if say good is equal to 0, uh, the probability of okay plus the probability of bad need to still equal 1, right? That is how we defined it. That is how we defined probability spaces, actually. So that distance between the point where uh, the vertex of all good reviews and the vertex of all okay reviews, they need to be exactly one. There needs to be exactly the distance of 1 unit between the two of them. So basically that's an equilateral triangle, right? Where every vertex is equally apart from each other, equidistant from each other. So a little bit of math will tell you that it is 0.5 comma root 3 by 2. This is for the foundation people, since we do have quite some time. So the distance between 2 points on a Cartesian plane is given by root of x1 minus x2 square plus y1 minus y2 square, right? So let's take this point. Let's take the distance between A and C. We're just verifying whether our point is exactly one. Our A point is exactly 1 unit away from our C point, right? So we'll get 0.0 minus 0.5. Let's take it as 1 by 2 square. It'll just be 1, so we can remove the square root, and 0 minus root 3 by 4, root 3 by 2 whole square, which gives us 1 by 4 plus 3 by 4, which is 1. So we've determined that this distance is in fact 1, which means we can now say that we can say that if B is 0, which is if all we have absolutely no good reviews, we still have a probability space where we have the probabilities still add up to 1, right? So what and everything inside this triangle also makes sure that the same thing is happening. And now let's talk about what the x and y coordinates mean here. So the x and y coordinates here are kind of a weighted function. So we're kind of taking a weighted average. So the probabilities that we're assigning each of the categories act like a weight. So me saying that we'll have more good reviews than bad reviews is a weight, right? So that weight will pull the probabilities here, right, towards the good corner. If I say that all of them are equally likely, it'll pull them to the center. Okay, so let's look at what this looks like. Are you guys able to see my screen? All right, I see. Okay.
Yeah, ma'am. Yeah.
All right, great. So we can see here that these are so S, T, and U here are the number of reviews we're getting, good, bad, and okay, respectively. And you can see here that A is 0, comma 0, B is 1, comma 0, and C is 0.5, comma root 3 by 2. Uh, and then we're defining the probabilities to be the mean. Again, that is a probability distribution we've assumed. And so we can kind of, so that is our kind of prior assumptions. And let's see what happens when we change the data, right? So let's say we've gotten all good reviews, and you can see, so the purple lines where they intersect is where we're at on the x and y coordinate plane. Okay, so let's say we've only had good reviews, no bad reviews, no okay reviews, so we'll obviously be at the origin, we'll be at A. But let's say we've gotten some bad reviews, so we can kind of move across this x-axis, and say we want to see what it would look like if we had only bad reviews. This is what it would look like. So x and y intersect at 1. Then let's say we had let's say we want to move across through the line that says we got no bad reviews, only okay and good. So we would kind of see this here, right? So if we had a lot of okay reviews, we would get closer and closer to C. If we had no good reviews, just all okay reviews, we would be somewhere here on the, well, we'll be on the C vertex. What happens when you have an equal number of all reviews, right? So that would be, say we got 20 good reviews, 20 bad reviews, and 20 okay reviews. So you can see that this is, would anyone like to guess what kind of center it is of a triangle? Because there are multiple types of centers, right? So there's an in-center, centroid. Would anyone like to guess what center this is?
Median.
Okay, it's
All are same for a equilateral triangle.
well, true, but sort of, so if you look at it, this is the center of the mass of the uh, triangle. So this is more related to physics, but it's also called the centroid of the equilateral triangle. So yeah, that's where you would find all of them being equally likely. Uh, so yeah, that's, so let's do a quick recap of what we've done so far. So the first thing we said was that new data should be used to update prior beliefs, not replace them. And we do that. So that is called the Bayesian thinking um, method of well, it's also a bit of a philosophical uh, tool almost, wherein it's more accurate than just seeing new data as in isolation. So that is Bayesian thinking. That's where Bayes' theorem comes into play. How this update occurs is defined by the beta distribution. We update it by kind of fiddling with the beta parameters, which are alpha and beta, and if we want to kind of extrapolate it to multiple dimensions, we call this a Dirichlet distribution. Again, the parameters of which we can kind of fiddle with to figure out basically what works best. So yeah, thank you so much for listening, and especially so for joining in on Diwali. I'm so grateful that you guys came down and gave your uh, very precious break to join in here. And I also would like to thank Pi Square for this incredible opportunity, because as a dual degree student, I don't get a lot of opportunities to meet my fellow students at IIT Madras and share the cool new things that I'm learning. But this was quite fun. Coincidentally, my entire presentation got deleted like half an hour before this was supposed to start. So I had a bit of a better presentation for you, ready for you guys. But I think what we've gotten through was adequate. And also, there's a form that you guys need to fill. Uh, I'll just put that into the uh, this into the chat. Just give me a second. This is a feedback form, and you guys need to fill this so that you can get your certificates. Uh, so just so make sure you do that, get your certificate. You guys can reach out to me on LinkedIn if you guys want to talk. Again, I'm probably just as old as you guys are, so don't call me ma'am, or just talk like I'm one of your peers, because I truly am, and I think I can learn far more than you can learn from me at times. So yeah, that's the end of my session. Uh, if you guys have any questions now, I suppose. I actually have another call to be on in like 5 minutes, so we're gonna have to be a little quick about that. Someone's asking me to share my LinkedIn ID. You can just search me up. I'm Tanishka Wagh on LinkedIn. You should be able to find me without problems. But yeah, do you guys have any questions? Anything to add to uh, the discussion, perhaps? Yeah, that's my LinkedIn. You guys can reach out to me, and I'll be down to talk to you guys. If anyone wants to send their questions, they can do so on LinkedIn as well. I'm available. All right. All right, then I think we can wrap up.